So this video is going to take a look at ideal gas law and stoichiometry. Ideal gas law, as we saw in our last lab, is related by PV equals nRT. P is pressure, V is volume, N is moles, T is your temperature, and R is your constant. That constant will be given to you, the 0.08206. Notice the units: atmospheres, liters, Kelvin per mole. Those are the units you need to have your various quantities in. If you have a pressure other than atmospheres, you will need to convert it. These are the conditions under which you would expect to have an ideal gas. And we see ideal gases when we are at lower pressures and higher temperatures. And basically, as long as it's below 1 atmosphere, we can use the ideal gas law and feel pretty confident about the volume or temperature that we're trying to determine. Or if we were trying to determine pressure, any pressure that we would calculate that would be below 1 atmosphere. So just to review ideal gas law, we're going to look at one example from both sides of the equation. So this one we're going to solve for pressure. We have 2 moles of helium gas with a volume of 34.5 liters that's at a temperature of 22.5 Celsius. What would be its pressure? So P equal V equals nRT. So divide both sides by volume. We get P is equal to nRT over volume. N is our moles, so that's going to be the 2 moles. R is our constant. Notice how I put the units both on the top and the bottom so you can see where the units cancel out. We have to convert our temperature to Kelvin, so that's how we get to 95.7. There's our volume in liters. The moles go away, the liters go away, the Kelvin goes away, and that leaves me with atmospheres. And that gives me a pressure of 1.41 atmospheres. So this gas is not quite behaving ideally. It's over 1 atmosphere, but it's relatively close, so we're going to go ahead and go with it. There's a correction you can do to account for real gases versus ideal gases that we'll see a little bit later on towards the end of the chapter. This sample of argon gas has a volume of 750 milliliters. It's at a temperature of negative 5.3 degrees Celsius and a pressure of 90.5 kPa. We want to know what its mass is. To find mass, we need to find a quantity we can measure. So we're going to or a quantity we can calculate and then convert into grams, which is what we can measure, and that would be the moles. So if we take our ideal gas law and we solve for N, we would get PV over RT. So we're going to substitute in our pressure. I did convert my pressure from kPa to atmosphere, since that's what my R units are in. I converted my volume in milliliters to liters. I substituted in my R. This time the units for the bottom half of the R move up to the numerator. And I converted my temperature to Kelvin. So the atmospheres cancel, the liters cancel, and the Kelvins cancel, leaving me with moles, 0.03. And then to find the grams, I would need to multiply it by the molar mass of argon, which is 39.95. And when the moles cancel out, I'm left with 1.2 grams. So when you're using the ideal gas law, you can actually solve for a couple of identifying quantities about a substance, or quantities that can be used to help you identify a substance. Molar mass is grams per mole, and as we saw in our lab, you can use the ideal gas law to solve for moles and divide it into the grams to get molar mass. Well, you can actually just solve for molar mass straight out if you substitute the grams into your ideal gas law equation. And you will get that M&Ms are great over a pint of vanilla, which is why I have the ice cream cone over here. G for mass, R for constant, T for temperature, divided by pressure and volume. Since density is mass per volume, and if we look up here, we can see in the molar mass equation that we have both mass in the G and volume in the V on the bottom. We can solve for density by saying that molar mass times pressure over the constant times temperature would give me density. So you can actually set up your molar mass equation in terms of density as well. In this example, we're going to solve for the molar mass of an unknown gas. We're given the mass 6.15 grams. We're given the volume 2.500 liters, the pressure 115 kPa, and the temperature 10 degrees Celsius. So molar mass, M&Ms are great over a pint of vanilla. Our mass is a 6.1. Sorry, I hit the pause. Our mass is the 6.15 grams. Our constant is the 0.08206 atmosphere liters per Kelvin moles. Our temperature when we add 273 is 283 Kelvin. We need to convert the 115 kPa to atmosphere, so we get the 1.13 atmospheres, and we get to keep the volume units, so the atmosphere units cancel out, the liter units cancel out, the Kelvin units cancel out, leaving me with grams per moles, which is the units that you would expect to have for molar mass. Multiply across and divide, and we get 51 grams per mole. If you need to pause this, I would do so now. And so our last example is going to be solving for density of ammonia gas at STP. STP, remember, gives us the standard temperature of 0 degrees Celsius and the pressure of 1 atmosphere. And we can use the molar mass of NH3 to get our grams per mole. So the molar mass of NH3 is 7. Again, it's 17.04 grams per mole. The pressure will be 1. Our R is 0.08206. And then the temperature will be 273 Kelvin. Moles cancel out, grams cancel out, grams do not cancel out, atmospheres cancel out, and Kelvin cancels out, leaving me with grams per liter, which is an appropriate set of units for density, mass per volume. If you need to pause, I would do so now. And then the last part of this video is going to take a look at stoichiometry. Just remember that when we are at STP, we do have a molar volume that we can use to relate the temperature and pressure to a set volume, 22.4 liters. If we are not under STP conditions, like we were in our lab, we had to use Dalton's law of partial pressures to get the pressure of our gas, and then use our ideal gas law to find the quantity we were looking for. And you could do that in the opposite manner as well. So you will not necessarily be able to just do a straight stoichiometry problem to go from a quantity to a volume. You may have to use ideal gas law or another gas law in order to help you get to where you're trying to find. In this particular example, we do get to use STP. This should be a review. In our Dalton's law video, we'll do some with non-STP conditions. Here we have calcium oxide. Quicklime is made by decomposing calcium carbonate. That carbon dioxide is also produced. We have 3.25 grams of calcium carbonate that was decomposed, and we want to know what the volume of carbon dioxide was that was made. So first we're going to turn our reactants into products. We're going to write calcium carbonate and convert it into calcium oxide and carbon dioxide. This is a balanced equation, so we have a 1-to-1 ratio of our reactants to products. Start with our given amount, 3.25 grams of calcium carbonate. We're going to convert from grams of calcium carbonate to volume of CO2. We didn't specify units, so we're just going to leave it in liters to help out with our conversion factor. Grams will need molar mass, so we'll calculate the molar mass of calcium carbonate. And that's 100.09. This 1 comes from the coefficient relating calcium carbonate, soon to be related to CO2. Liters will get 22.4, and it too will have a 1 in front because it's a 1-to-1 ratio. The grams of calcium carbonate cancel out, leaving me with liters of CO2. I multiply across and divide, and I get that I have a volume of 0.727 liters. If you need to pause, I would do so now. Alright, and that's the end of this particular video, and the next one's going to look at Dalton's law and some other characteristics of gases.